Welcome to the video on section 8.2, which is homogeneous linear systems. Finally, we're getting to the point where we're actually going to solve these linear systems of differential equations. We did all of the matrix review and some of the new stuff with finding eigenvalues and eigenvectors. We looked at the preliminary theory for homogeneous and non-homogeneous systems, and now we're actually going to solve. We are going to have to think back to eigenvectors, and just as a note, we are only solving homogeneous systems. So in the last video, we took a look at the theory behind non-homogeneous systems and how you would solve them, but we're not actually going to do that. So if we return to example 1 from 8.1, we saw this system right here, which we wrote using matrices, and then we had these two different solutions. And I believe we showed that these two different solutions are linearly independent, which we talked about. We can then use superposition to form a general solution. Now what we notice is that both of these solutions have the form of two constants, e to some power of t. But what's really important is that power is an eigenvalue. And so the question is this always true? Well, let's consider a general system. So let's consider a general system written as x prime is equal to a times x. Well, we need an expression for this x prime and this x. So let's look at this general solution that we have above. That general solution we said is some vector k times e to the lambda t, which means x prime then is going to be k lambda e to the lambda t. So if we substitute those in, we're going to get k lambda e to the lambda t is equal to a k e to the lambda t. Well, e to the lambda t is never 0, so I'm going to divide that out, which gives me k times lambda is equal to a times k. This should look familiar. So if we move everything over to one side and we factor out that k, then we're going to have a subtract lambda I multiplied by k equals 0. Again, we've talked about this before, but lambda is a constant. A is a matrix, so I can't take a matrix and subtract a constant. So I have to take that constant and multiply by I to make sure I actually get it subtracted. This is now a matrix that we are multiplying by our vector 0, or our k vector, to get 0. So then remember, when we talked about this before, this has two solutions. The first one is that k can be the 0 vector, and this is the trivial solution that we don't care about. Or the other option is that the determinant of a subtract lambda times I is equal to 0, which means this matrix right here, a subtract lambda I, is non-invertible. Where this leads us to then, so our conclusion from all of this work is that x is equal to k e to the lambda t will be a solution of that system x prime is equal to ax if and only if, so that's what this means, if and only if lambda is an eigenvalue of a, and k is an eigenvector corresponding to lambda. So this leads us to our first theorem. The theorem says, let lambda 1 to lambda m be distinct real eigenvalues of the coefficient matrix A in our system. Then k1 to kn are the corresponding eigenvectors. Then the general solution is x is equal to c1 k1 e to the lambda 1t all the way up to cn kn e to the lambda n t. And again, that is the general solution. So what that tells us, or what that's leading us to, is that if we have this system, we're going to need to find the eigenvalues, and as long as they're distinct and real, we can use the eigenvectors to form this general solution. So let's take a look at the first example. Here is the system that we're going to be solving. So first thing that we want to do is we want to be able to write this system using matrices. So we get x prime is equal to 1/2, 9, 1/2, 2 times x. So that tells us that our matrix A is that coefficient matrix of 1/2, 9, 1/2, and 2. So to find our eigenvalues, we're going to take the determinant of the matrix A subtract lambda I. And so we're taking this A and we're subtracting lambda times I, which is this matrix. So that gives us 1/2 subtract lambda, 9, 1/2, and 2 subtract lambda. And we want that to be equal to 0. So then finding that determinant, we get lambda squared, subtract 5 over 2 lambda, add 1, subtract 9 over 2 is equal to 0. So lambda squared, subtract 5 over 2 lambda, subtract 7 over 2 is equal to 0. If I factor that, I get lambda subtract 7 over 2, and lambda add 1 is equal to 0, which therefore tells me that my eigenvalues are 7 over 2 and -1. Okay, so going back to that theorem we wrote on the previous page, we have two eigenvalues, and they're both distinct. Well, both distinct and both real. So now we need to find the corresponding eigenvectors. So I'm going to start with the first eigenvalue of that 7 over 2. And so if you remember, what we're going to do is we're going to take matrix A and subtract 7 over 2i, and we're going to augment with 0. So when we do that, we get -3, 9, 1/2, -3 over 2, augmented with 0. So I'm going to do two steps in one. The first thing I'm going to do is I'm going to multiply the first row by -1/3. So when I do, I get 1, -3, 0. And then when I do that, I'm going to take that first row that I have, and I'm going to multiply by -1/2, and I'm going to add it to the second row. So that second row is the 1/2, -3 over 2. So when I do that, I have 1, -3, 0, and the bottom row just becomes all zeros. So then if we remember how to read this line right here, we're looking for K1 and K2 to find our eigenvector. So we get K1 subtract 3K2 is equal to 0. So our K1 then is equal to 3K2. So what I can do then is I can choose whatever value I want for K2, like 1. So my K1 then will be 3. So this is my first eigenvector that corresponds to that first eigenvalue. So next thing that I'm going to do is I know that my second eigenvalue is -1. So again, we're taking A, we're adding I, and we're augmenting with 0. So when we do that, we get 3 over 2, 9, 1/2, 3, augmented with 0. So I'm going to do two steps in one. I know that I'm going to be multiplying that first row by 2/3. And then currently what I'm going to do is if I multiply that first row by -1/3, I can add it to the second row. Okay, so I'm going to multiply, I'm going to do this part first, multiply the first row by -1/3 and add it to the second row. The reason I do that is it gives me a 0 and then another 0. Now if I multiply the first row by 2/3, I'm going to get 1 and a 6. So then I get K1, add 6, K2 is equal to 0. So K1 is equal to -6, K2. So that gives me my second eigenvector then. I can choose whatever I want for K2. So then that makes K1 -6. Okay, so where I'm going with this then is I have an eigenvalue, the corresponding eigenvector, eigenvalue, the corresponding eigenvector. So I can use all of this now using that theorem to write the general solution. So the general solution to our system is x equals C1 times 3, 1, e to the 7 over 2t, add C2 times -6, 1, e to the -t. So this is the general solution of our first homogeneous system. So that is the first case. Now let's look at what happens if we have eigenvalues that are not distinct. or maybe not real. That's what we'll get to also. So now we're going to look at what happens when we have repeated eigenvalues. When we have repeated eigenvalues, there's actually two cases. First one, for some n by n matrices, we might find m linearly independent eigenvectors k1 to km corresponding to just one eigenvalue of multiplicity m. Then the general solution will contain c1 k1 e to the lambda 1t, add c2 k2 e to the lambda 1t, so that's the same eigenvalue, all the way up to cm km e to the lambda 1t. So this would be the case where this one eigenvalue has multiplicity or has m different eigenvectors, and so we will have a component for each of those different eigenvectors. On the other hand, though, what if there's only one eigenvector that is corresponding to that eigenvalue of multiplicity m? Then there will be m linearly independent solutions of the following. So x1 is going to be k11 e to the lambda 1t. x2 then will be k of 21 t e to the lambda 1t, and that should look familiar, plus k of 22 e to the lambda 1t. That t is for the multiplicity, and then we get all the way down to x of m, which is k of m1, and then t will be to the power m minus 1 over m subtract 1 factorial e to the lambda 1t, all the way to k of mm e to the lambda 1t. And keeping note here, these k11, k21, k of m1, these are all the same eigenvector. Okay, so I'm going to be honest with you. I look at this and I just have a big blank in my mind. This just doesn't really connect for me. And so for me, what's helpful is to see this in action. And so that's what I think we should do. So let's take a look at this example too. First thing that we're going to do is find those eigenvalues, of course. So I'm going to look at the determinant of a subtract lambda I, and I want that to be equal to 0. So I'm going to have 1 subtract lambda, 1 subtract lambda, 1 subtract lambda, negative 2, 2, negative 2, negative 2, 2, negative 2. Now, I am not going to review finding this determinant. We did that before. That's not the point of this video. So if you need to review finding this determinant, look back at the matrix review video. So we end up, when we multiply everything out and factor, this is what we get. So we see that our first and second eigenvalues are the same at -1, and then our third one ends up being 5. Okay, so let's find those eigenvectors. The question is, how many eigenvectors are we going to get from this eigenvalue that has multiplicity 2? So what we're going to do, if you remember, is we're going to take a look at the matrix A add 1 times I, and we're going to augment with 0. So that gives us 2, negative 2, 2, negative 2, 2, negative 2, 2, negative 2, 2, augmented with 0, 0, 0. Hopefully you can see all 3 of those rows are constant multiples of each other. So we're going to get 0, 0, 0 for the second and third rows. That top row, if I divide by 2, I get negative 1, 1, 1, negative 1, 1, rather. So again, to read this, we get k1 subtract k2 add k3 is equal to 0. So k1 then is k2 subtract k3. So that means that k1 depends on both k2 and k3. So first I can choose k2 to be 1 and k3 to be 0, which gives me an eigenvector of 1, 1, 0. Then separately, maybe I choose k2 and k3 to both be 1, which gives me an eigenvector then of 0, 1, 1. So we'll see then that this eigenvalue that had multiplicity 2 gave us two different eigenvectors. And these, you should see, are linearly independent. Okay, so let's keep moving. So what we do next then is let's take a look at our last eigenvalue, which is 5. So we're going to be taking a look at the matrix A subtract 5i augmented with 0. And so that matrix is -4, -2, 2, -2, -4, -2, 2, -2, -4, augmented with 0, 0, 0. Okay, so this one is going to be a smidge bit more work. I'm not going to easily get a 1 here. So instead what I want to do is I want to swap these two. And so when I do that, what I'm going to do is I'm going to divide this last row by 2. And I'm going to divide this top row by -2. And so that will give me 1, -1, -2. And this will give me 2, 1, -1. And that middle row, I'm also going to divide by -2 to get 1, 2, 1. Okay, so what I'm going to do next is I'm going to take this first row, multiply by -1, and I'm going to add it to the second row so that I can get a 0 here. If I take that first row and I multiply it by -2 and add it to the third row, I'm going to get a 0 there. So where that leads me to then is I get 1, -1, -2, so that stays the same. And then the second row becomes 0, 3, 3. Third row becomes 0, 3, 3. So we should be able to see then I can get zeros in the last row. That second row I'm going to divide by 3 to give myself 0, 1, 1. So the last thing that I'm going to do is I'm going to get a 0 here just to make the solving a little bit easier. And so I'm going to take negative the second row and I'm going to add it to the first row. So when we do that on the first row, I'm going to get 0, 1, 0, -1. Second row is unchanged. Third row is zeros. So where that leaves me with then, looking at these two, I get K1 is equal to K3, and my K2 is -K3. So my third eigenvector then, I could choose whatever I want for K3, like maybe a 1. So then I'll get 1 and a -1. Okay, so I have a 3 by 3 system, and I got 3 different eigenvectors, so that's great. My general solution then is just going to be C1, that 1, 1, 0 of e to the -t, and then I get C2 with that second eigenvector, which is 0, 1, 1, e to the -t, and then I have my third eigenvector, 1, -1, 1 of e to the 5t. So there we go. That is the first case of having repeated eigenvalues, so multiplicity 2, where it gave us, though, 2 different eigenvectors. What we need to consider next is what happens when we get multiplicity 2 for an eigenvalue, but we don't get 2 separate eigenvectors, we just get 1. So let's take a look at that example. This one I want you to start out on your own. In a minute, I want you to pause the video, and first thing I want you to do is find the eigenvalue. Now, 2 by 2 system, you should have 2 eigenvalues. I'm going to tell you that you just end up with 1 that has multiplicity 2. And from that 1 eigenvalue, I want you to find the eigenvector. Again, 2 by 2 system, we should have 2 eigenvectors, but this eigenvalue is only going to give us 1. So you're not going to be able to find the general solution, but you should be able to find 1 eigenvalue, 1 eigenvector, and then come back with me. So pause the video now and see how far you can get. Okay, let's see how we did. We're looking at the determinant of the matrix A subtract lambda I, and we want that determinant to be 0. So we end up with 3 subtract lambda, -18, 2, and -9 subtract lambda, and we want that to be equal to 0. I'm just going to tell you, I'm not going to show all of the work. If you want to go back to reviewing finding eigenvalues and eigenvectors, make sure you look at the matrix review video. But if you end up multiplying and finding this determinant, you end up with lambda add 3 squared is equal to 0. So our eigenvalues end up being the same of just -3. So next what we should have done then is looked at the matrix A add 3i, and we should have augmented with 0. So when you do that, we get 6, negative 18, 2, negative 6, augmented with 0. Hopefully you can see that these two rows are constant multiples of each other. So if we simplify the first one, and then the second one, we're just going to get zeros since they're constant multiples. So this tells us that k1 is equal to 3k2. So my first eigenvector, if I choose k2 to be 1, k1 will be 3 then. So at this point, we know that we should have two eigenvectors. We only have one. So at this point, we only have one solution, and that solution is the 3, 1, e to the negative 3t. We need to find a second solution. So to do that, we know that our second solution is going to be of the form x2, which will be k t e to the lambda 1t, add p e to the lambda 1t. So this portion of the solution comes from the eigenvector that we already know. P is what we need to find. So to do that, to find P, what we're going to do is we are going to solve A add 3i times P augmented with K. So here's what that's going to look like. We are going to start with the A add 3i that we did above. So we have 6, negative 18, 2, and negative 6. But now, instead of augmenting with zeros, we augment with k. So we augment with this eigenvector that we already found, so the 3, 1. So what I'm going to notice is, again, they're still constant multiples, so I still get zeros on this bottom row. But now on that top row, when I divide by 6, I get 1, negative 3, and 1/2. So what I get then is that P1 is equal to 1/2 add 3 times P2. So if I choose P2 to be 0, then I get my vector P to be 1/2, 0. So where that leads us to then is that our second solution, again, this first part comes from the solution we already know. So that's going to be 3, 1 t e to the negative 3t. And then I have 1/2, 0 e to the negative 3t. So all of this then leads to our general solution, which is going to be x equals c1 x1 add c2 x2. Sorry, this is a 1. So we get x is equal to c1 3, 1 e to the negative 3t, add c2 times that entire solution we just found, which is the 3, 1 t e to the negative 3t, add 1/2, 0 e to the negative 3t. Are you having fun yet? I hope so. Let's move on. Oh, look, we have another example. At this point, you should be thinking, what else do we have to do? Well, we've looked at distinct real eigenvalues. We looked at real eigenvalues that have multiplicity more than 1. Only thing we haven't done yet is complex eigenvalues. So that's what we're going to do now. So taking a look at this system, if I look at the determinant like we have been of a subtract lambda I that we want to be 0, if we set that up, we get 6 subtract lambda, negative 1, 5, 4 subtract lambda. So if we multiply all of that out, I will tell you we get lambda squared subtract 10 lambda add 29 is equal to 0. Solving that quadratic using the quadratic formula, we get lambda is equal to 5 plus or minus 2i. So this is the case now where we have two eigenvalues. They're different, but they're complex. So if we treat the first one to be that 5 add 2i, so we're going to take a look at the matrix then, A subtract lambda 1i augmented with 0. So when we do that, I'm taking 6 subtract my eigenvalue, 4 subtract my eigenvalue, so I get 1 subtract 2i and negative 1. I have 5, and then negative 1 subtract 2i, augmented with 0. So what I'm going to do is if I take the first row and I multiply by 5, and then I take the second row and I multiply by 1 subtract 2i, if you trust me, what ends up happening is you get zeros on that bottom row. The top row, we just keep the same. So what that shows me then is that k2 is 1 subtract 2i times k1. So I get my first eigenvector then if I choose k1 to be 1. K2 then is 1 subtract 2i. Okay, so now let's do something similar with the other root. So my other root then is 5 subtract 2i. So that becomes then 1 add 2i, negative 1, 5, and negative 1 add 2i, all augmented with 0. So similar idea, I'm going to take row 1, multiply by 5, and I'll subtract 1 add 2i times row 2. Again, we're going to get zeros for the bottom row. This time the top row, I'm going to get 1 add 2i and a negative 1. So this tells me that k2 is equal to 1 add 2i times k1. So my second eigenvector then ends up being 1 and 1 plus 2i. So ultimately where this leads me to then is this general solution x, where I get c1, 1 minus 2i, times e to the 5 plus 2i t, and c2, 1 plus 2i, e to the 5 minus 2i times t. What I want us to notice is that in our eigenvectors, the second components are conjugates. This leads us to another theorem. If we have complex eigenvalues, then k1 e to the lambda 1 t will be a solution, and the conjugate of that eigenvector and e to the conjugate of the eigenvalue will be the second solution. So that's our theorem. Now, of course, we take a look at these solutions and think, well, I don't want these complex solutions or these complex eigenvalues. We often want our solution in terms of real functions. So how do we do that? Okay, well, let's just start with, we know that we have this eigenvalue of alpha plus beta I. So what that gives us then is our k1 e to the lambda 1t can be expressed as k1 e to the alpha add beta I times t. Now what we're going to do is we're going to split this power up into the real and the imaginary parts. So this gives us k1 e to the alpha t multiplied by e to the beta it. Now if we think back, throw back to last unit when we were solving homogeneous linear differential equations, just one equation, not a system, we are able to re-express a term like this using Euler's formula. And so we're going to do that again. So this becomes then k1 e to the alpha t, and we get cosine of beta t add I times sine of beta t. So that looks a little bit better. Similarly, what we're going to do, if we look at the conjugate of e to the conjugate of t, it's just k1, that's the conjugate. That gives us the conjugate of e to the alpha t, and we will get cosine of beta t subtract I times sine of beta t. Okay, this looks a little bit better, but we still have these imaginary terms. So we want to eliminate the imaginary terms. And so what we're going to do is we are going to take a look at 1/2 if we have the sum of k1 e to the lambda 1t and then the conjugate of e to the conjugate of t. So where that gets us is we have 1/2 of k1 add its conjugate, e to the alpha t times cosine of beta t. And then we would have negative I over 2 of negative k1 add k1 conjugate, e to the alpha t sine of beta t. Okay, and you're probably like, where did I get that from? Well, I took this, added this with the 1/2. Now, what if we did I over 2 times negative k1 e to the lambda 1t, add conjugate e to the conjugate t? What would we get? Well, we would get I over 2 times negative k1, add the conjugate, e to the alpha t cosine of beta t, add 1/2 k1, add conjugate, e to the alpha t sine of beta t. And again, you can confirm that these two just come from what is underlined below. So all we did was add these two, apply I over 2, so multiply by I over 2 and bring together those terms that were similar. Okay, so at this point, let's take a pause and see, where are we at? Where has this led us to? So one question you probably have is why I chose these. So let's take a look to the side of why I would do that. If I have z is equal to a add bi, and then I have the conjugate of z, which is a subtract bi, notice that if I do 1/2 z add its conjugate, I'm going to get 1/2 times 2a which is just a. And if I do 1/2 negative z add its conjugate, like we did here, I'm going to get I over 2 times negative 2bi, which, simplifying, gives us just b. So really, going back to what we have highlighted, this is really just a, another way of expressing a. This is really just another way of expressing b. When we did all of that, we ended up with these coefficients, which you can go to verify are real. So if you take this eigenvector, add its conjugate, and you multiply by I over 2, you're going to get something that's real. So now all of our coefficients are real. And so what we end up with is we end up with this coefficient b1, really it's a vector, that is 1/2 of k1 add its conjugate. And we end up with b2, which is I over 2 times negative k1, again, and add its conjugate. So this comes from our real coefficients. This comes from our imaginary coefficients. So what we've done is derive what we need to do when we have complex eigenvalues. So let's take a look at what this looks like in terms of a theorem, and then we'll look at some examples. So here is the formalized version of what we just derived. If alpha 1 is equal to a add I times beta is an eigenvalue of our homogeneous system, and we used b1 to be 1/2 k1, which is a vector, add the conjugate of k1, again as a vector, and b2 is I over 2 times negative k1, again a vector, and k1 conjugate, again a vector. Then our first solution is b1 cosine of beta t subtract b2 sine of beta t e to the alpha t, and x2 is b2 cosine of beta t, add b1 sine of beta t, times e to the alpha t, are linearly independent solutions of our homogeneous system. And you can go back and verify that this is exactly what we got on the previous page. So if we take these two, add them together, this is what we got. Again, if we take these two, add them together, and apply I over 2, this is what we got. And so the notation then is B1 is the real parts of K1, and B2 is the imaginary parts of K1. So let's return to that example that we did before. We found our first eigenvalue to be 5 add 2i. And then when we found our eigenvector, we found it to be 1 and 1 subtract 2i. And so we can write that as the real and the imaginary parts. This is 1, 1, add I times 0, negative 2. So that tells us then that our B1, which is the real parts of K1, is the 1, 1. And our B2 then, which is the imaginary parts of K1, that is our 0, negative 2. So what that leads us to then is that our general solution x, again, going up to here, is going to be C1 times 1, 1 cosine of 2t subtract 0, negative 2 sine of 2t e to the 5t. Add to that C2 times 0, negative 2, it's a negative 2, cosine of 2t. Add 1, 1 sine of 2t e to the 5t. So all of this is our general solution. So at this point, you might need to pause and take a look back through, figure out where did I get these numbers before you keep going. And finally, through all of this, we have one last example. So when you're ready, let's take a look at this last example. So find the general solution of this homogeneous system. So if I take a look at our determinant of a subtract lambda I, and I want that determinant to be 0, I'm going to get 2 subtract lambda, 8, negative 1, negative 2 subtract lambda. I want that to be equal to 0. The determinant ends up being lambda squared add 4 is equal to 0. So our eigenvalues are plus or minus 2i. So then if we write those in terms of alpha and beta, our lambda 1 is equal to 0, add 2i, and our lambda 2 is 0, subtract 2i. So I'm going to start with my lambda 1, which is that 2i. So what I'm going to do is I'm going to take a subtract lambda I and augment with 0. And so we end up with 2 subtract 2i, 8, negative 1, and negative 2 subtract 2i. And so I'm just going to make things a little bit friendlier for myself. What I'm going to do is I'm going to take this second row and I'm going to multiply it by a negative 1 and make it my first row. So I have 1 and 2 add 2i. And so then I'm going to get my 2 subtract 2i and 8 down here. So then what I'm going to do is if I take 2 subtract 2i and multiply it by row 1, and then I subtract row 2, you can verify it, but I'm just going to tell you in row 2 you're going to get zeros. And the top row stays the same. So what that leads us to then is reading this top row, we know that K1 is negative 2 add 2i times K2. So I get my eigenvector to be 2 add 2i and negative 1. Again, that's just one possible vector. So if I write that then, my real part is 2 and negative 1, and my imaginary part is 2 and 0. So this is my B1, and this is my B2. So that's all we need to write the general solution. And so my general solution then ends up being C1. Again, look at my parts. I get 2 negative 1 cosine of 2t, subtract 2, 0 sine of 2t, and then I have e to the 0t. I wanted to show that. You don't need to put that because that's just 1. Add C2, and I get 2, 0 cosine of 2t. Add 2, negative 1 sine of 2t. Again, e to the 0t, which is just 1. So that is our general solution. Okay, I know that was a long video. Thank you for sticking with me. You might need to go back, review some of the examples that we've done, or go back and rewatch some parts of the video, but you should know how to solve a homogeneous system when we get distinct real eigenvalues, when we get real repeated eigenvalues, and then when we get complex eigenvalues. So thanks for watching, and I'll see you next time.